So I'll start off with some presentation slides. We looked at the confusion matrix last week, so I won't talk about that, but you'll be able to reference it. And then we'll spend the rest of our time working on the exercises. And I'll probably help fill in some of the code, but I do think the best resource for you is going to be the sklearn cheat sheet. You can also use Google. You know, how to use split up the training and testing data is something you can always reference. It's not something that you need to memorize. Okay, so some of this I'm going to skip through, but I wanted to give us an overarching sense of what we're doing here. So just going back to last week, we saw decision boundaries, vertical and horizontal lines that could be used to separate the data based on some kind of target variable. So this was an example using age and income. And we looked at kind of the best vertical line. We started with this vertical line to separate the individuals based on their income. And then within those partitions, we looked at separations based on age. And we're trying to, minimize the entropy within each of these segments. And that allows us to build the tree, and then we're able to figure out our feature importance. And from there, we're able to make some kind of recommendation based on the target variable of interest, right? So we could say, for example, if this is the, I think this is a bank data set where we're looking at whether or not someone will default on a loan, we can figure out from the decision tree which variables are going to help us identify those customers who are most likely to be a write-off, default on their loan, and then the business can come up with certain interventions that they might do based on an evaluation of those important features. Okay. The next chapter, the chapter 4, was all about linear classifiers, which basically take us from the vertical and horizontal partitions into the realm of using some kind of a function to build the model. Okay. So an early stage of this could be building this concept. We could think about, instead of drawing a vertical and horizontal line, we could take a look at a diagonal line that is in fact a function, and that line could be our decision boundary. And we could do something like, determine the class plus, or this is not, but it's supposed to be a minus, plus or minus, if the value of the function, when some values of the predictors are plugged in, if that value is greater than 0, we might make one decision about how to classify an individual. If the value is less than 0, then we might make another decision. So that, yeah, I think that's much to say about that. How do we choose the best line is another thing to consider. So in the chapter that you read, there was a lot of discussion about the ways to optimize the linear classifier. And as you can see, there are lots of different ways that this line could be determined. But the way that that is usually decided upon is based on some form of optimization, which is related to what's often called a loss function or objective function. Okay. So I just wanted to give you a little bit of a sense for what is an objective or a loss function. You see that term come up a lot in the context of linear modeling. So a loss function really has to do with how we choose to penalize errors. So everything you're going to see here, and this is sort of abstract representation of something. But it's actually not too difficult to understand. So a loss function is going to look at it. So all it is doing is looking at differences between actual values and predicted values. So to understand the symbols, a y usually represents an actual value, whereas f of x is representing a predicted value. So if we were thinking about something like, if we're predicting taxi fares, which is something that we would look at, the y would represent an actual taxi fare for an individual rider of a taxi, and the f of x would represent a predicted taxi fare for a rider in a taxi. So what you can see is there are lots of different ways that this can be done. The most common approach for a loss function and optimizing our linear model is using a least squares method. So the squared difference between the actual values and the observed values, right? So that's this one right here. And this one is so common, but I have to say it's not necessarily the best. Part of the reason it's common is because that was originally done by hand before computers were available. And then all of the software packages that we use tend to use this squared loss by default. And so we just tend to rely on it. So linear regression and logistic regression and another method called support vector machines are all really basic techniques for linear modeling, but they are different. So they all fall into the realm of linear classifiers, but they differ in terms of how they penalize errors. Okay. And the goal when we're fitting a model, we want to find the model that minimizes the loss function as much as possible. Okay? So when you do like a least squares regression line for a scatter plot, you're fitting a model that minimizes those differences between the line, the predicted line, and the observed values of your target variable. We focus a lot on logistic regression because it is one of the most popular tools. And the regression is in quotes because when we hear the word regression, we usually think of predicting a numerical outcome. But we should really be thinking about logistic regression as more of a classification scenario. So classification and regression are different because classification involves predicting a category, a yes or no, right? Yes, the customer will turn, or no, they won't turn. Whereas regression predicts a numerical outcome, like the house price or a taxi fare. So with logistic regression, the model does produce a numeric estimate, but it's a probability of class, an individual belonging to a particular class. So that's why I think it's helpful to think about logistic modeling as more of a classification scenario, because the values of our target variable are categorical when you're doing logistic regression. So you're not going to do a logistic regression problem when you're trying to predict something numerical that could vary for each individual. So the way logistic regression is described is it is estimating the probability of class estimate, which is, in a sense, it is a numeric quantity, but it's related to a categorical class. So a logistic regression model should actually be called a class probability estimation model and not a regression model. I think the authors of our book are feeling a little bit fussy about this distinction. They don't like the fact that logistic regression is called logistic regression. So we're going to be working with logistic regression in our exercises today to predict the probability that an employee will leave a company. Okay? So, will leave or won't leave a company, that's our categorical class. And then the numerical prediction is the probability of the individual belonging to one class or the other. I'm going to skip over this. So support vector machines, you may run across those. Support vector machines use linear classifiers, but there's a margin involved. So instead of using this diagonal line as a divider, there's a margin that's used as a divider. And the error penalties are related to how far the individual observations deviate from that margin. So that's something we won't cover as much in this class, but we'll reference it from time to time. Okay, so I just wanted to go over this really quickly. So a lot of times, as I've said, we don't just want a yes or no prediction of whether an instance belongs to the class, but we want to know, we want to have some sense of which individuals are more or less likely to belong to a class. So that's the direction we're going in today. And it allows us a little bit more customization when we are formulating our business actions that might be necessary. So for example, we might want to know which customers are most likely to respond to an offer. Okay? Which customers are most likely to leave when the telecommunications company when their contracts expire. And why this might be useful to have a probability instead of simply a yes or no is because there might be only a certain amount of resources available for intervening in those cases where, say, a customer is likely to respond to an offer. Okay? So if we can look at probabilities of a customer responding to an offer, we can make some decisions about, which customers, which collection of customers should we target with the offers. Okay? So that way you could decide, well, how far do I go down the list? And those probabilities would give you the option to rank customers. You can say, all right, well, I have enough resources to target the top, 400 customers. So then you could go down the list according to likelihood of responding to the offer and cut off the top 400 customers that way. So that could be really useful. So probability could be helpful with determining ranks. I think I already discussed this. This is just another scenario, right? So with the mega telco, if we identify the counts or transactions to be likely to be defrauded, this is just another example. The director of the fraud control operation could, may want the analysts to focus not just on the cases that are most likely to be fraud, but on the accounts where the expected monetary loss is higher. So in that case, you might want to estimate the actual probability of fraud. So this is another example. Lastly, last comment here, why might we use linear models versus tree induction? This is going to be the kind of, these are considerations that will start to develop as we go through more and more different types of machine learning models. So, like I said, before you decide on a model, you usually have to try a lot of different models. And some of the considerations are not necessarily related to the model performance. Sometimes it depends on who is receiving your information. So tree models, for example, are very easy to interpret. So if you are presenting to some managers or executives who don't have a statistics background, they're going to understand the results of a tree model much more easily. There's some features of the data that will determine whether a linear model or a tree model performs better. And one of those features has to do with how smooth the underlying phenomenon is. So, for example, when we looked at our first diagram, it was fairly easy to draw vertical and horizontal lines. But it may be the case where there's like a curve separating the individuals in the data set. And if that's the case, it's a little harder to use the tree induction to partition the individuals. So that feature of the data could make a tree model perform less well. Right? So same thing, how nonlinear the underlying phenomenon is. And if there's a lot of data engineering needed to apply linear models, that could be a reason to choose a tree diagram. So data engineering could be things like changing the scale of your data. So we're going to run into examples where we have data measured on really, really different scales. So for example, age and income is something that will come into play when we're looking at the employee attrition data. With tree models, it's actually not necessary to scale your data, so it's all measured on the same numerical scale. But with a lot of linear models, it's necessary to scale your data. That means to turn everything into a z-score. So rather than having age and income, you would have measurements that are z-scores. So if it's age, the measurements would be how many standard deviations above or below the average age someone is. So that would be your whole column of standardized age. And for income, you would have a column of standardized income, which would be measuring, in terms of z-scores, how many standard deviations above or below the average income somebody is. And that ensures that variables that have really large values, like in the case of income, make sure that they don't dominate the model, because the mathematics behind fitting the model are better implemented when everything is on the same scale. So that's an example of feature engineering. Sometimes we have to, we need the predictor variables to be normally distributed or more symmetrically distributed, again, to avoid problems with the model fit. And that's necessary with linear models. So sometimes we might have to take a log transformation, take a logarithm of every one of our values in the data set, usually just the predictor variables. So that's feature engineering, and that isn't necessary with tree induction. So these are just some characteristics that are worth considering when you're deciding between models. Some of this you may know in advance, and you may be able to discover from the exploratory data analysis that you do. Other times you don't know, and you're just going to have to try a few different models to see which one performs best. And when we're talking about performance, I know we haven't gotten into the topic of model performance yet and evaluating model performance. We've done a little bit of that, but we will do much more. what we're going to start to see today is something you saw in the data camp courses, where we look at the performance of a model on the training data and then again on the testing data. Okay, so